What? Now you're just doing crazy talk. Okay, next, you have the title down. I want you to write this down. And the spacing matters. So this needs to be on the bottom, 1s, and then you go to 2s, and then there's 2s and 2p, and 2p should be a little higher than 2s. And then there's 3s, and the 3p should be a little higher than the 3s, and the 3d should be a little higher than the 3p. But this is really important. The 4s should be in between these two. So their relative placement matters. The number of dashes matter. You need to draw this. No, it would not. I deliberately have not given you a printout. Because you need to be able to draw this from memory to work on problems. Do I have a printout I could give you? Yes. Am I going to? No, because it is not educationally appropriate right now. 3D is above 4S. One S? Oh, not. No bottom axis. It's just spaced out so we can see it. We could put them all right here. This is just energy. What is the bottom axis is the dashes to show the number that fit, but our spacing is arbitrary. It's for ease of our use. So there is no bottom axis. Don't take a picture. You can't see it? Sit there. Sit there. Why can't you see? No, stop it. No, seriously, like, do you need glasses? Run back to your house? Do you need glasses? I could make them darker. Seven, yeah. So one dash with the 1S, 2S, 2P. Hazel, would you like to put a desk right where you're standing? Because it's my classroom. We could, like, rearrange things. Yeah. We could shuffle it. We could also work. I mean, I have you in rows because it's just convenient. But, I mean, we could, like, bring more people closer by making the rows together. Yeah. I used to put only 2 rows. They're very close. They're all next to each other with a path down the middle separated. But Mr. Brian kept wrecking it, so I stopped doing that after a while. But he only teaches here 1 block, so. Whereas at that time he taught there like 4 blocks. Pardon? I don't think so. Teaches AP Chem. Yeah, he's a chemist. Yeah. Okay, listen, colleagues. Hazel, would you like at your own desk? But when you go back to your seat, will you be able to see? Is it just the yellow? Well, I also didn't think about it in case someone was colorblind. I just color-coded. I think, who is it? There's one teacher. They still don't know what their house color is. Legasic, yeah. So colorblind. I've diagnosed at least, I think it's 4 students with color blindness in grade 10 over the past number of years. Not right now. We've got stuff to do, but in grade 10, sometimes you have more time because they need time to absorb. Whereas here, we just throw it at you. We just throw it, and we move on. Yeah, we do have that. It's coming up. It's like hopefully by the end of next week. Test day. Test day. That's a relaxing day. You don't learn anything new. You just get to tell me what you know. Probably. Yeah. Okay. While we're waiting for the last to finish up, I'm going to ask. Now, I'm going to make you do this. I'm going to do the first one. I can wait a couple seconds. Don't take. Draw it. Like. No, I'll stop. I'm stopping. I don't know. And this is not something you walk up and ask someone, but you can say, "Hey, I heard you were colorblind. Is it okay if I ask you a question?" And then do that. They are. It is mostly guys. Because it's a sexually selected trait. It's carried on the X chromosome. What are the chromosomes? If you're female, what chromosomes do you have? Men are XY. It is only carried on the X. It is not carried on the Y. So if you have a bad gene and you're male and it's on the X, you're guaranteed to have whatever deficiency that is because you only have one copy. But if you're a female, you have two copies. So you have both genes, then you're colorblind as a female. Yeah. No. Yeah, and you're still good. In fact, if you have one as a female and the other one's fine, you actually have super color vision. That the mutated gene adds a little bit of different information. So if you just have that one, you're colorblind. But if you have it with a regular gene, some of the mutated ones actually provide, and you can tell apart colors that nobody else can. You have a greater range. Yeah. Pardon? You can test yourself in your color ranges, but not on a computer. Because the computer, you exceed the abilities on the color capabilities of most computers, unless you're working with those $15,000 art ones that photographers use. Yeah. Okay. I'm not going to go on. I'm just going to write my first example down. Ian, please do not comment on other people. I'm going to use calcium as my example. Yeah, and I'm going to ask someone in the room how many electrons it has. Get out your periodic tables. So have your periodic tables out because you're going to have to do that for other elements as well. Okay. So Class Dojo has Sam, are you done? You don't want to tell me? Okay. And then Samantha, how many electrons does calcium have? You were looking at carbon, Ca, to your left. Two would be helium. Oh, 20. Does everybody know about the second periodic table in your data booklet? Ian? You just answered for everybody. I should ask this. I'm assuming some of you don't know. So this is your regular periodic table. Right? Everybody has that? If you turn over the page, it's the one there's another one in alphabetical order. So if I say, hey, look up calcium, you can go, oh, Ca, 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 and then calcium is right there. It tells you it's element 20, so there's your number of protons. But if you wanted to see it on the periodic table, then you can go, oh. And now you can count it along and find 20 really quickly, which is there. And that really helps when you're asked for something weird like osmium, and you're like, I don't know where that is. You just look it up on the alphabetical side. Okay, 20 electrons. And I'm going to ask someone else to give me, what would the classic Bohr model mean? So if we had the classic Bohr model, because we're going to compare, we would have 20 protons, and I don't care about the neutrons because they're not charged. Yager, what would the electronic structure in Bohr look like? Two, eight, eight. Yep, looks good. Any disagreements? Excellent. So here's how we put it in. This is our electronic structures chart. This is what quantum chemists use to figure out the electronic structure. They just draw this out quickly. This is one of the reasons I didn't give it to you as a handout, is you do need to be able to draw it from memory. I will show you a trick to generate the order so you don't have to remember, in case you're like, oh, does 3D come after 4S or is it above? There's a way that you can do it so that you can generate it again. And I'll show you that later. Right now I just wanted you to draw it. And now I'm going to put in the electrons. I'll put them in blue. There are 20 electrons. There's a couple of rules. Number one, electrons are lazy. Little Joey electron is not going to climb all the way up the hill. Little Joey electron is going to be at the bottom of the hill. It's much easier to be at the bottom of the hill. Also, in order for them to be compatible, you have to make their spins opposite. I don't have a nice analogy for that, other than electrons don't like being near each other unless they have opposite spins. We show this by using an arrow that's been cut in half. Angular momentum, literally spinning. Yeah. And they spin forever. They just have this as a property. If I take an arrow and I cut it in half, then I have two half arrows, right? So we've decided in chemistry that this means spin up and this means spin down. We use half arrows. So our first electron goes in, and I put them in an order. Spin up. Now the other one doesn't want to climb, so spin down, and that one's full. 2 electrons per slot. 2. Next one up. I don't want to climb further, so spin up. The only spot I can go, same energy level, spin down. I've used up 4 electrons. Those are half arrows. Yes, first energy level, second energy level, third energy level, fourth energy level. We started from the bottom and we're working our way up. Yeah. What does this mean? So this means spin down. And this means spin up. Nope, it means if they're at the same energy level, they have to have opposite spins. So if I did this, that would never happen. Electrons do not like each other if they have the same spin. The only way they can fit together is if we give them opposite spins. And then only 2 will fit. Because if we tried to add another one, like stuff it in there, it would have the same spin of one of them and they'd kick it out. One of the ways to think about it is that it's not like one of them spin up and one of them's always spin down. It's a bit like magnets. If you have a magnet and you put it near another magnet, it'll just rotate to be the opposite of the other one so that they can fit. The same with these electrons. So they'll change their spin to be the opposite of their partner. Also, we don't fill it up this way. And electrons are negatively charged. Oh, Sam, yes? I don't think I said it's starting down. No. We started at the bottom, not started like down spin. We started down here. That's independent of spin. Let's not do on the test. Let's just look at this for right now. No. No, nope. Focus. Okay. Well, I don't want to hear on the test. Yeah, maybe. Yeah, that's absolutely the thing. And you can generally assume that anything I do can be a question on a test. Yep. Yes. No, you go to, so this is like climbing. You would take the path of least resistance. So this is only a little bit higher, so you're going to go here. And then when we put another one in, is it going to go in the same orbital? No. Let's go to here. Because they have the same energy, and they don't want to be together because they are both negatively charged. And the next one will go here. Depends if you have questions. So in the same orbital, suborbital, they have to have different spins. But these have solved that by just going into different orbitals. Yes? No, none of them do. And honestly, if I did this, doesn't matter. Doesn't matter until they're all just separated out. Hands, although I can barely see Hazel. Hazel? Jensa? Jensa? So I'm going to start right at the beginning. We're just filling in the orbitals. How many electrons do we have, Jensa? Right in calcium. 20. How many fit in the first one? 2. So I have to fit 1, and then the only other spot I can go, while still being the lowest possible spot, is in here. So I have to make it opposite. Okay? And what's the next one? 2s. So I fill that. We'll get to that, but there are. Just let me finish this, and I'll show you where the 8 are. Okay? Sam and Hazel, you guys could work together, but I'm trying to see Jensa. So where would the other electron go, Jensa? Down, right there. Now for this one, they're all the same energy. So it doesn't matter which one we fill first. Which one do you want to fill? Pick one. Left one. Up or down? Okay. No. The next one, it's not going to go in the same one because they're both negative. So if they have a choice, they'll just spread out. When you walk in a bathroom and there's someone in a stall or at a urinal, do you pick the one right next to them? No. Nobody picks the one right next to them. You sit in a stall next to someone farting away? There's only 2. But I mean, like you're at like a stadium or something. There's a huge amount. You walk in. Let's not argue about the example. It's a hypothetical. I'm assuming. I Okay, fair enough. I will. If you can come up with another example in which people would like to space out and avoid each other, I'll use that. Now back, Jensa. Where's the next one going to go? Yes, which one? In the same one? It would have to if it goes in here, but it doesn't have to go in here. Why not one of these? We could do that. They have options. Yeah. Okay. Ian, you have to put up your hand and you can't just yell. Yes. Oh, are you talking about this up and down? Neither one is more energy or less. Well, if you have a question, you have to put up your hand. This is lower energy because it's further down. This is down spin, which is completely different. Don't confuse down in the English language. If I use that term, I'm now regretting it because this is further down the graph, so this is lower potential energy. But up spin and down spin both have the exact same amount of energy. Okay? It's more like north and south magnets than different energy. No, it's just how I write them. So we could do it like this. No big deal. Yes, Jacob. No. Jacob. Ian, no more talking. I will forbid you from talking for the class if you can't be patient. Yes. Yeah. So like this S is still a sphere. 2S, that's another sphere. These P's are your 3 dumbbells. And we're filling each one up with 2 electrons. This is another sphere. Here's our 3 dumbbells. Badly drawn. And these are our butterflies. And then and all of these are laying on top of each other, yes, at slightly different energies. So we have a total of 20 electrons. We've only put 2, 4, 5, and 6. Sam? Yeah. The key part here is we're spreading them out first. When the energy is the same, Sam, where would the next one go? Up or down doesn't matter, but where would it go? On the third one. So the next one, do you want it to go down or up? Okay. Now we have another one here. What does it have to be, given this? Has to be, Jensa? Up. And it will go in one of these. We have 20 total. We're just filling it up. Yep. I added another electron, and I'm going to keep going till I run out of my 20. Question? So once it's full, they have to be opposite when you fill it up like this. Does that make sense? Yes, Ian. A couple of them. Yep. Yep. Well, if I did 7, I would go. Let's do it to the side of it, but in a different color. 1, 2, 3, 4, 5, 6, 7. And these don't matter in that they're separated. So I could easily have done up, down, down because they're on separate orbitals. Okay? So if there's 2 of them, the spin matters. They have to be opposite. But if there's just one of them, it really doesn't matter. Yes? What? I was answering Ian's question. Yeah. No. That was just... I am adding... how many electrons do I have here? There. And then we're going to keep going till we get to 20. Yes. That will not happen. Don't. No, that we run out of elements. Like literally, it's built into our universe. We don't make elements that large. So we're at 10, 11, 12, because there was nowhere else to go. 13, 14, 15, 16, 17, 18. Now, where do we go next? 17, 18. Those of you who said 3D, the 4s energy level is lower. So it takes a shortcut and goes to the 4s. It's just closer. Yeah, and there's one extra. So you could, if this had 21 electrons, say I didn't do calcium, I did scandium, then it would go here, and then the next one would go there, and then be the end. Yes, who said that? There you go. Okay. Now, a key part here is that it didn't finish the third energy level. Every time we changed the type of orbital, when we went from spheres to dumbbells, the amount of energy rose. When we go from dumbbells to butterflies, the amount of energy rose. We went from P to D. However, the 4s is just that much above the 3s, so it will just fill up next. So although this is the third energy level, it fills up after part of the fourth energy level. Yep, go. So it will go to 4s. It'll jump to 3D because that's in between. Oh, okay, yeah. And then it will go to 4p. And then 5s. And then 4D, and it keeps going from there. And at this point, we start running out of elements. We don't have stable elements, so that's why we don't have to worry about orbitals beyond F. And I didn't go up to 5F because I'm not going to give you that. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is all of them. Now, 288. This is how Bohr got that. How many electrons are in there? 2. How many electrons are in this energy level? 8. Now, this didn't get filled, so how many are in the third energy level for Bohr? 8. And then it started this one, so that started off with 2, but then it's going to fill up these 10. And that's why you're eventually, once you fill up this and that, you're going to get 18. So 2, 8, 8, 18 is correct in Bohr, but he didn't know why. These energy levels underneath all of that were filling up in an order that just wasn't intuitive. Would probably be the best way to put it. I'm going to pull those out now because I think it makes the diagram really messy. There we go. So whenever we want to fill this up, we have to do it in a particular order, which is why I started off saying the spacing is really important. We have to remember which order it goes in, and then we can generate the electronic structure for any atom. Some of the rules that I've just said are right here then. So write these down below. Electrons are filled bottom up. Electrons are separated in the same suborbital until they must pair. There, make that a little better. And when you have to pair them, they have to be in opposite spins. As you go up in orbitals and you get further and further from the nucleus, it has more potential energy in the same way that a rock at the top of a mountain has more potential energy. If it fell to the bottom, it's releasing a lot of its potential energy. Now, for a rock, it translates it to kinetic. For an electron, it translates it to radiation. So when an electron drops, we get light. This is not element decay. This is just light, like radiation. And it's often visible light. It's not dangerous radiation. Just a form of electromagnetic radiation. And it can release it in sometimes different ways. So if you take a compound and you heat it up, the electrons will actually jump up into a higher energy level. So they'll fill an empty orbital because they have a lot of potential energy. Then when they drop back down, they'll release light. Did you do a lab last year in which you put chemical compounds like on a loop or on a wooden stick, and you got pretty colors out of it, purples and greens and all that kind of stuff? Yeah, that's showing the electrons jumping up, which isn't a color, but as soon as they fall back down, that releases the color. That's the energy of the spacing that they fell. Okay, so that's calcium. Are we good with calcium? Okay. And I know it seems a little arcane. We've got a lot of terminology. We've got a few rules about how we fill it up. But it is just a straight graph, and we fill it up with order every time. It doesn't change. I do find it to be this when I first encountered it, they didn't do this in my high school chemistry. But when I encountered it in university, at first it was like, oh my God, this is like really complicated. And then it was like one of the easiest sections because it repeats itself over and over again. I want you to draw it again in pen. Pen. Not pen. And I want you to also have a pencil ready. So draw it again in pen, but have a pencil ready. Because we're going to use this one more than once. So you're going to be doing stuff on this and then erasing it and doing it again. Yeah, sure. If you want to make it neat and use a ruler, that's fine. But sketching, that's fine too. Again, and what matters is the spacing. And the 3D is above the 4S. Let me make sure that it still is. Yeah. I'm going to add some more lines. Do not panic. These are not lines you have to add, but just to show you. Let's pick a color that's not on there. Green's not on there. So this comes out to about there. That comes out to about there. That comes out to about there. However, if you put this in, as long as it's in there somewhere, you don't have to be exactly that amount. If you put it halfway, that's fine too. If you put this one a little above, as long as below. It's the relative order that I care about, that you have the 1s below the 2s, below the 2p, below the 3s, below the 3p, below the 4s, then 3d, then 4p, then 5s, then 4d. So it's the order that matters. And I guarantee you, after you've done it a couple of times, this will be the easiest section you do all year. Because now that we have the diagram, we're going to do something with the diagram. Because the diagram is showing your work. The diagram is not the work itself. The diagram is the method by which you get it. So we want the electronic structure, and we've shown it graphically, but we also write it out, and like you would write it out with a typewriter. And I'm going to start off doing carbon. In fact, I'm just going to note here all the ones we're going to do. Argon, magnesium, sulfur, strontium, and krypton. I'll just wait till everybody has this drawn in pen. And I could probably set up. I'm going to do carbon. And then that way, because I'm going to show you what I want, because you don't know what I want yet out of it. Element, and then electronic structure. And then, let's see, I'm going to do this, grab that, let's do this. Nope. Once you've drawn that structure, you can abandon your pen and use pencil for everything else, as you should, because of course nobody uses pen for notes. Right? Nobody uses pen for notes. Excellent, well done. Nobody should be using pen for notes. And I'll do this and I'll add to that. So, the first one I'm going to do is going to be carbon. I am going to ask someone how many electrons carbon has, because that's good practice. Ian Cooper, 6. So I've got 6 electrons. Ian, guide me through how to put them in this diagram. Now, this is the part you do in pencil.
In 1s, 2 in 2s, and then it doesn't matter the order, but 2 more in 2p in separate orders.
Excellent, well done. Now, this is the electronic structure as we would write it out, because we don't show graphs every time. That would take too long. What we do is we say, so for carbon, it is 1s. That's the first energy level. How many electrons are in that energy level? 2. So I put a 2 here. It doesn't mean squared. It means 2 electrons. But you do superscripted. What is the next orbital? 2s. How many electrons are in it? 2. What is the next orbital? 2p2. And that is the entire electronic structure. Oops. Don't do that, Mr. Neufeld. That is the entire electronic structure for carbon. Now, if I had this and it was like this, it would be 1s2, 2s2, 2p5. So you just change that number for how many electrons. That tells me the electronic structure. We are doing it for neutral atoms only right now, so it's just the number of electrons off the periodic table. I would like you to do it for all of those. And I'm going to randomly call on people to come up to the tablet to do it on here. So carbon is 1s2, 2s2, 2p2. Well, you know when if you're watching Star Trek or Star Wars and they say a bunch of gobbledygook you don't understand? That's why they do that, because it will sound sciencey. Except the difference is that this actually has meaning. Yes? Oh, have you done this before? They've already done this. Curses. No, you're not allowed. Right now, you cannot use core notation. Yeah. Yeah, no core notation. Yeah. Shocks, no core notation. But what is the next step I'm going to do is I'm going to show you core notation. No. That's Lewis dot diagrams. Okay. Now I'm just going to write these down here. So I've got argon, magnesium, sulfur, I think was next, strontium, and then the Kr. What? No. In order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So you do it in the order that they get filled. Sorry, what was that, Ian? Thank goodness. It's just that, yeah, because although I was accused, are you going to lie about other stuff? By its very nature, quantum has to include familiar trappings of Bohr, because Bohr was just a simpler model. Okay? So I'm going to call on some people to come up to do these. We're going to start with argon. Magnesium's a metal. Strontium's a metal. Oh, okay. Sorry. Nope. Yep. Nope. Let's go. I'm going to take out strontium. And I'm going to add in, where was strontium? Let's do yttrium. It's right beside strontium, so if you did it, you only have to do one extra thing. There you go. And I'm going to ask Max to do the first one here. So Max, you've got argon whenever you're ready. And Jensa has magnesium. And then I'm going to leave the other one so everybody can just hope that they get it. And I'm in the way. I'm sorry.
Wait, am I just writing?
You're just writing it like 1s2, 2s2. Is it making more sense now? Yeah. Excellent. You can rest your hand on it. It's not a touch screen. It's a pen screen. Pardon? Yeah. Just one hint. Don't click the buttons. They do the weird things. Sorry? Yeah. Well, I find the most confusing part of this is the format and how they do it, not actually what we're doing. Yeah, no, it's probably, it should seem like a foreign language. Yeah. Woo! 3p6, that makes sense. So after Jensa, let's go with is Morgan. And then why don't we say Jacob, yttrium. Why? Why? Jacob, would you object to doing krypton? Okay, you're krypton, and Ian wants to do Y. Oh, Jensa? It's not technically wrong at all, but it is weirdly out of format. So I'm just going to say, don't put commas in. There's no commas and no spaces. It's just spaces. No, everybody will ignore the spaces. In fact, spaces can make it easier to read. That's not a big deal. But the commas are different. Oh, you pressed the button here. The buttons on that I haven't fixed yet. It's the buttons on this. If you press a button, it says E. I don't know why. There you go. Yes, Sam. Samantha. That's the number of electrons in it. So which one is this one that you've just done? Okay, so this is 1s. So you haven't labeled it, though. Okay, so you're just using that. So this is 1s, and how many electrons in there? So that's why that 2 is there. How many electrons are in this 2p? 6, and that's why there should be a 6 there. But you're missing something here, because it should go from 1s to 2s and then 2p. So this should be below that, or add another 1s there, I think. Are you just missing it? I think you're just missing the 1s. So that 1s2, 2s2, 2p6, 3s2. Does that make sense? Okay. Yeah? Let's do 2p6. Jensa, what's your magnesium? There's something wrong with that one. How many electrons does magnesium have? And how many do you have in there? 10. You need 2 more. Where would they go? Yeah. He is a pro. Beautiful. Well, as was hinted, we are going to do something called core notation, which takes a lot of the pardon? Can you do it? No, you don't. You don't know what that is. Shh. No, you don't. Shh. And whoa. Lawnmower?
That's what your like brother's name is.
No nicknames.
It made an E.
Yeah, it does that if you press the button.
Oh.
If you press this button, it makes E's, or that button. One of them does it. I don't know why.
Oh.
So I have to go in and fix it somewhere in the settings. There you go. Now,
Do you have like extra practice, like questions that we can
yeah, the Hebden. Yeah, don't worry, they're coming. As of today, I can now move the list. Boop.
No, but I mean like I missed it. You have like these kind of things. Like these kind of practice stuff, but this isn't like practice. Like on paper, yeah.
Like a worksheet. We're doing it, and then Hebden. Because part of it is like, I don't know if you've noticed, but in grade 11 you have to do more of your work in prep. Because I have to include a lot of content in the class to make sure you're ready for not just Chem 12, and it's not, you have to be ready for university because university is a big threat. There's a lot to know in chemistry. And when I say we're scratching the surface, I really mean we're scratching the surface. So they're going to try and get you to go faster and faster, and I'm just trying to get you up there. So more of that does have to be in prep. And so the Hebden is your worksheet. It's pre-printed worksheet. There's your worksheet. Oh, no. Oh, yeah. Yeah. Oh, do you want to know the method that they use in university to prioritize that? Do your chemistry first. Yeah, there you go. You're welcome. So what I would like you to do now, and I'm going to post it. Yeah.
Can I leave for like 3 minutes?
Why?
Because my field hospital is at 1:45.
What? Quantum. Okay. I have just assigned you a class because I can't get to everybody and see what they're doing. I saw someone out and we fixed their little mistake. I would like to see yours. Class Dojo, I just assigned it as an assignment to take a pic. I would like you to take a picture of yours and include the workings. If you erased them all, then fine. I just want to say take a picture, upload it to the Class Dojo that was just posted. And if you don't have one coming up, we'll charge it. Is it an Apple phone? Yeah. There. Grab that. Plug it in somewhere. Okay. Hold it. Options. Connect students. Show classroom instructions. Nope, that's not it. Nope. Where did I get this? No.
What's on the board? If you take a picture of what we wrote, like as that, and take a picture of it, is that okay?
1 second, because I'm trying to connect someone. So I just. Live. Sorry? Oh no, you're added. What I want is your QR code, and I don't want that one. Yeah, Class Dojo. We found some of those didn't work. Where was it? Classroom, students, class story, messages, student login, show home instructions, get the printouts. Here we go. Sorry, they put it in multiple spots. So, live. There you go. Scan that when it asks you to do a thing. There. Does it find you? Okay. And then Morgan. That's yours. There you go. Yes. So I'm looking at the quantum electronic structure. Woo! And I've got approve all. And sure. So I'm still waiting for 11 others. Just can you just add another one? Oh, it looks lovely, Jensa. I think I can delete it. There, I deleted it for you, Jensa. Sorry? Well, take it and take it again. I probably deleted it at the time and told you what to fix on it. No, there you go. There you go. It doesn't seem to be there yet. Once yours has been approved, I will say you can go. Yep. Yeah. Yeah, that's all. I just want to see what your work was like. Just so I can whip through and see if there's like any obvious glaring errors that I need fixing next day. No, that's okay, because that's not actually an error, but that's more like, yeah, it's more like using two spaces in between a period and the next sentence now in a paragraph. Nobody does that anymore, so it's weird. Yeah, yeah. I'm approving them all. Approved. Thank you. Thank you. Thank you. Oh, thank you very much. Did it worked? Excellent. The quiz only counts if it helps you. Is the way to think about it. So if you do worse on your test, then the quiz still counts, because why wouldn't I? Yeah. Yeah. Yeah, and then we'll go, you'll get it back. People have reported that person absolutely did write the quiz, so I'm going to go to the library and find it, mark them, then I'll be giving them all back next class. Yeah, you'll get it back, and I'll show you exactly where. Hello. Oh, yeah, yeah, yeah. Okay, that's good. I have to reload and then approve all the time as soon as they're, because yes, I will. Hold it. In fact, I've approved yours already. It just hasn't popped up on yours. Reload your screen. Excellent. Hmm?
Mine is good.
Oh, did you put yours in? Oh, no? Yep, yours is good. Yep. Emiliano. Yeah, yours is good. It should show up as approved. Yep. You just probably usually have to reload. Pardon? Sorry, did someone have a question?
Put the K one over there because I didn't have enough.
Oh, I'll see that. Yeah. This is not marked. This is for me to quickly check if there's any glaring errors. Well, I'll get to it in just 1 second. If you've got at least one, you're good.
I didn't SR.
Oh, that's fine. As long as you did it correctly, it's all good. I just want to check if there's any serious errors.
And it says it's pending. Oh no, actually.
It just got approved. If there's a delay between you sending it and then I don't see it right away, and then and then my approving it, there's a delay back until you see that message.
The last two that we did from last class are
Oh, are they? Oh yeah, I haven't approved those yet. That's mostly just because I haven't gone back in. It looks like it. Hold it. Approve all. There. Hold it. Some looks like some took it today.
I took it today because you.
Yeah. Yep. All good. All good. Thank you.
And I don't even know how I did that bad in the test because I already took this, so I'm not proud of myself.
Well, I think probably, and I don't mark them knowing who people are. So what I do is I mark everybody's question 1, then everybody's question 2, and that way I'm trying to be as objective as possible. What I would suspect, it's probably, I'm guessing, question 1, which was sort of 6 marks. It's a lot of graphing, so how you set it up, but maybe not. We'll see. Yes, hold it. I thought you were talking about something else. I thought you were talking about your quiz. Yeah, I got it, and I will approve it. You are good. You'll get the quiz, and the purpose of the quiz is to know what you're doing wrong. And so I like having a quiz before a test because you need that feedback before you don't want to get it wrong on the test. Because that's your big assessment. So yeah, you'll get it back, and we'll go over it. You're welcome, and it should be very next class. You're welcome.